So today's video is about the application of sigma. And in all honesty, this really isn't even going to take it to its fullest today. What we're in essence doing is we're starting with those baby steps again in incorporating these summations with a more generalized way of looking at them. Where we're headed with this is we're eventually going to take these Riemann sums and make them in more of a generic way so that we can actually do it for any subdivision. And I know that seems rather abstract at this time, but we'll get there, I promise you that. And what's going to happen is we're going to be joining together these summation things you've been working on in the homework packets along with the Riemann sums that we've been doing in class and in practice. So before I can do that, I want to explain to you these key things that you see on the left of your screen. Each of these equations that you see to the left here obviously were developed by seeing some patterns. And the truth is, you're not going to be able to totally find them yourself, okay? And so you're going to be using them, have this on like a reference sheet someplace, have them on a card or someplace in your homework packet that you can easily see them. But these three equations that you have in front of you, at this point, you're going to have to just believe me that this is true. I'm just going to show you that it works with just a couple of examples so you can understand where this is headed. But to actually find them yourself, well, you're going to have to believe me because you actually need some work that we only do in calculus. In fact, the calculus group will be doing this themselves here in the coming days of how to find these equations. Now, that being said, let me just show you how these work. Let us say that we had the summation as k goes from 1, and let's say it went to 5 of 1. Now, what that means is you're going to plug 1 in, you're going to plug 2 in, 3 in, 4 in, and 5 in, and you're going to add those results together, right? Well, when we do this equation, when I plug 1 in, there's no k. There's no place that's, this says k equals. There's no k, so that means when I plug that 1 in, or the first term, is just 1. When you plug 2 in, again, there's no k to put that in, so it's just another 1. And that would mean that you're going to add that 5 different times, because that's what that means. Each time, you would just get 1 plus 1 plus 1 plus 1. And when you add those together, guess what you get? 5. And that's really what they're saying. Whatever number is up here, what if this was a 6? Well, then that would mean there were 6 ones, so that would be 6. Again, that number is the same here. Pretty obvious, I guess, in that sense. Now let's look at the next one and what that means. Again, I'm not going to show you how to find this equation because, again, it takes a little bit more finesse than what you're ready for, I guess, at this point. We'll be doing it in a week or so, one method to find it, but this is just one equation you should know. What it means, in essence, is instead of actually doing this summation, for example, if this said 3, then that would mean that I'm going to plug 1 in, I'm going to plug 2 in, I'm going to plug 3 in, and I'm going to get this, and that would mean that it equals 6. Or I could instead see that it actually works in this equation. In other words, that this should equal the same thing as 1/2 of 3 squared plus 1/2 times 3, which would be 9 over 2 plus 3 over 2, which is 12 over 2, which is, ta-da, 6. Now, you don't really appreciate the beauty of that, except if I said U30. Does anyone in here, especially since you're not using calculators, want to go 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, all the way up to 30, add all those numbers together, and then get your sum? Or if I said, 30 or whatever number here, and I'll prove it to you using a smaller number because 30 is kind of extensive. So let me just use 10, okay? Again, what that would mean is you're going to do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 and plus 10. So just to do that math relatively quickly, I guess, I'm just going to group some things together. So I've got 4 and 6, which make 10. I've got 5, 3, and 2, which also make 10. I have 1 and 9, which make another 10. So then what I have left is 7 plus 8, which is 15, and then the last 10. So 10, 20, 30, 40, 55. That's what I should get for an answer. Well, let's see if that's what I actually get. That would mean that I do 1/2 of 10 squared plus 1/2 of 10. Well, 10 squared is 100, divided by 2 is 50, and half of 10 is 5. Now, I was obviously able to group those things together in 10 relatively quickly, and maybe you still don't appreciate it, but it's so much faster to do that. Certainly if I was doing the squares, 1, 4, 9, 16, 25, and I'm adding all those up together, it would be much faster if instead I knew, oh, hey, with 5, which is 1 plus 4, right, plus 9, plus 16, plus 25, that I could add these together, which is 55, or I could do 1/3 of 5 cubed plus 1/2 of 5 squared plus 1/6 of 5. So I just want you to see that that's how that's applied, and of course I would get 55 again. Now, that at least gives you hopefully a believable stance that yes, it is true that these work, and that's in essence what they're doing. So where we're headed with this is, how does that apply when we're looking at these sigmas, okay? So we've already learned in our homework assignment that we could put this 4 in front. And so that this, what I'm writing here, 4 summation of k, is the same thing as saying the summation of 4k. And by doing it in this way, now I can see, hey, I can replace the summation of k with this equation that I see right here. So I would put 4, and in place of that, put 1/2 n squared plus 1/2 n. And now I'm going to distribute the 4, which gives me 2n squared plus 2n. And that would be my answer. And that's all I'm looking for, is that you would write it in terms of n. Now let's try the next one as our last example here. I'm going to pull this 6 out in front and write it simply as the summation of k squared. I put a plus. I don't mean to do a plus, so excuse me here. I'm going to put minus 8 summation of k plus 7. Now, what do you think I'm going to put as my summation here? Because every single term gets that summation. Almost see it like a distributive in and of itself, because every term gets the summation, even the constant. And that's where the summation of 1 comes in. Yes, each of these should say from 1 to n. Admittedly, I get a little sloppy with that at times. You'll probably notice that as I do some examples, even in class. That I want you to understood that each one represents from k equals 1 to n, just as it says here in the problem. But what I'm looking for is, in place of the summation of k squared, is that you put 1/3 n cubed plus 1/2 n squared plus 1/6 n, whoops, sorry, I forgot my n, minus 8. And in place of the summation of k, I'm going to put 1/2 n squared plus 1/2 n plus 7. And in place of the summation of 1, I'm going to put n. Your steps that follow here is just basic algebra that you learned back in the day, you know, where you're distributing this through. Now, I do want to take this time to understand that these n's that we're talking about are on top. They're in the numerator. Some people actually would write this as n cubed divided by 3 plus n squared divided by 2 plus n over 6, just so that that confusion doesn't occur. So make sure that you are careful about this. So this would be 2n cubed. This would be 3n squared. This would be just n. Now remember, this is negative 8, so that'd be negative 4n squared, negative 4n plus 7n. And of course, just as you would expect, we're going to combine like terms, so that'd be 2n cubed. I have 3 minus 4, making negative n squared. 1n minus 4 makes a negative 3, plus 7 would make that 4n. And this is the equation or the expression I'm looking for in terms of n. That's what b would actually equal. So if it said, hey, you've got 5 subdivisions, all I would need to do is plug in 5 for n and not have to actually plug 5 into that whole equation, or 1, 2, 3, 4, 5 into that equation every single time and then figure out what it equals. I could simply figure out what it is in terms of n, like you see here using those substitutions, and then just plug in 5. So obviously much faster. This would be 125 times 2, or 250, minus 25 plus 20, right? So that's 245. Certainly much faster than plugging in 1, 2, 3, 4, 5, getting those results and then adding them together. So there you have it. That's the idea of this application of sigma, and how we're going to be using it later on. Well, you'll see that in the next video or in class.